So these are the only two things you're left with. Now, transition metals is you've got a thing called the D block elements. I'm just going to do a brief introduction first. Okay, you've got a thing which is called which is called D block elements. They're not transition metals, not all of them at least. Okay, D block elements are uh, I mean, you know where they are. It's you've got a periodic table. There's a the middle part, that's your D block element. Remember, that's not transition metals, TK. And then you have the other side. TK, that's group 3 to 7. Let me just get an actual periodic table just a second, because we would need that. As this one, here's your actual periodic table. So the middle part, TK, the middle part is known as the D block elements. Does anyone know why it's called the D block element?
They have a d subshell, like they have outermost electrons in a d subshell.
No, not the outermost.
Yes, sir. But they have like electrons in their d subshell. That's why.
TK, the last electron goes into a D subshell. So what were the other groups? This was your S block, and all of these, the other ones, up till group 8, that they were known as your P block. Okay. So remember, technically, this is not transition metals. This is D block elements. Um, so the last electron goes into D subshell. So if I pick any one of them, for example, if I pick copper, so how does the electronic configuration end for all of them? At least the first row. That you're going to have. I mean, this one would be 3D1,
Or yes, sir.
and the outermost would be 4s2. Okay. The next one, इसको थोड़ा ऊपर नीचे कर लेते हैं. अच्छा, so the next one would be 3D2 and 4s2. Then after that, you're going to have again 3D3, 4s2. उसके बाद that's chromium. That's chromium is your special case. It's not going to be 3D4, 4s2. It's actually going to be, I mean, it should have been 3D4, 4s2, but instead it's actually 3D5, 4s1. Okay, do you remember that? Is this clear?
Yes.
Okay, chromium's electronic configuration was chromium was an exception. So next one is again 3D5, 4s2. Next one after that, that's 3D6, 4s2. एक second, जल्दी से कर लें. So after that, you've got 3D7, 4s2. So what's the next exception? That's nickel would be 3D8 and 4s. And then you've got copper, which is going to be 3D9, 4s2, but it's not going to be 3D9, 4s2. It's actually going to be, क्या होगा? It's actually going to be 3D10, 4s1. And finally, you've got zinc, which is going to be 3D10, 4s2. ठीक है? So is this clear? By looking at the atom, you should know what the electronic configuration of that particular atom is. ठीक है? Is this clear?
Yes.
Yes, sir.
And you should know how to write the whole electronic configuration. Acha, so your D block element. Now, most of your D block is transition metals. Acha, so the question is, what is a transition metal then? Like, why do you classify some element as a transition metal? So most of them are like 92. So 90 to 80% of these elements are transition metals. Now, transition metal is a classification that's based on uncertain properties. So the definition of a transition metal is technically the definition of a transition metal. If anyone is going to ask you about this, it's this. Okay, it's an element that forms stable ions with incomplete d subshells. So an element or a d block element. I said that forms stable ions with incomplete d subshells. So remember two things. They have to form stable ions with incomplete d subshells. Okay, that's what a transition metal is. So the definition does not apply to the metal element itself, but it applies to the ion that that particular element is forming. So for example, now we know that iron is a transition metal. It's got how many electrons? 26. So the whole electronic configuration is 1s2, 2s2, 2p6, 3s2, 3p6. Then you're going to have 4s2, and then after that you're going to have 3d6. Okay, that's what iron looks like. So you're not going to look at iron's electronic configuration. You're going to look at the stable ions that iron would form. Does anyone know which stable ions are formed by iron?
So
Fe2 plus and
Fe3
Fe3
2.
plus.
Okay. So it's Fe2 plus and it's Fe3 plus. Okay. These are the common stable ions that we already know most of these ions. So the electronic configuration of Fe2 plus is that it's going to be if I write this as argon, okay, the whole thing up till 3p6. If that's argon, that's 18 electrons, right? So 3d6, so it's going to be 3d6, right? And Fe3 plus would be argon followed by 3d5, right? The outer electrons are going to get removed. The 4s would be removed, plus 2. The 4s would be removed from plus 2, and then there's going to be 1 going from 3d6 as well. So this is what your electronic configuration would look like. Is that clear? And is it a transition metal based on the definition? It is because the D subshell is incomplete in both of these cases. So hence it is a transition metal. Is that clear?
Okay, sir. Sir.
Okay. So make sure you know what the definition is. Same applies to cobalt. Cobalt, I think, is mostly 2 plus. And let me tell you the common oxidation states. I mean, you know the common oxidation state of most of them. Do you know what is the highest oxidation state of Mn? Does anyone know that? Like, what are the common oxidation states of Mn?
There is +7.
The KMnO4 is +7, right? There's MnO2 as well, that's +4. There's Mn2 plus as well. Iron is +2, +3. Cobalt mostly it's +2, +3. Copper is +2 and +1 as well. So you should have some idea, and I'm just going to so common oxidation states of, and we are only dealing with sorry, period 4. Because I've got a graph over here. TK, we can just copy this. So you need to have some idea, although most of you already know what the common oxidation states are. TK, at least for the first row. Zinc is +2. Copper can be +3 as well. Let me just check one more graph, just a second. Yeah, I need one. Yeah, this one. This one looks fine. Cobalt +2 +3 nickel. Yeah, I think where's iron? Iron is. Yeah, this one is the better one because it also tells you the most probable oxidation state. Second, let me copy this. So the most probable oxidation states. ठीक है, the highlighted ones are the most probable oxidation states. Scandium is +3. Titanium could be +3 +4. Vanadium, iron is +2 +3. Manganese is +2 +4 +7. So you need to have some idea about what the common oxidation states are. And so I'm going to, I'm going to highlight some of them. This is KMnO4. When do you think chromium forms a +6 oxidation state? Well, which compound in which chromium has a +6 oxidation state? कोई idea? Any idea? Any 1 minute? Mahin, Zaina, any idea?
Sir, can you
Like when does chromium have a +6 oxidation state?
like is K2CrO like is potassium dichromate in that
ठीक है,
case we'd have +6.
ठीक है, so you've got K2Cr2O7. ठीक है, that's where chromium has a +6 oxidation state. But anyways, you should remember this that which elements have which oxidation state. Previously, you had the data booklet with you, and but now you don't have the data booklet. The good thing about the data booklet was that it had the electrochemistry equations, the electrode potential equations. They were very helpful. For example, if you wanted to find out the common oxidation state of vanadium, you could have just looked at the the equations over here, and you would know that it's +2 and +3 is also getting formed. Over here, I think okay, it's probably +4. VO3 -1, that's +5. So you would have some idea about the common oxidation states. But now you don't have the table over here. I mean, it's not going to be printed next to the question. So now you don't have that help. So you have to remember some of these elements. Now that's the first thing. There are certain elements which are not going to have stable ions with incomplete d subshells. Some of those elements are scandium, zinc, for example. Zinc is not a transition metal. Why? Because simply put, it doesn't have an incomplete d subshell. If you form a zinc ion, right? Zinc is argon followed by 3d10n, 4s2. So when it forms a +2 ion, and that's the only ion that it usually forms. So it's got a complete 3D subshell. Is that clear? So zinc is not a transition metal. ये बात clear है?
Yes, sir.
Yes, sir.
ठीक है, this one is complete D subshell. Similarly, scandium is not transition. Scandium is also not transition because what is the oxidation state of scandium? That's +3, right? Now the original scandium is argon followed by I think 3d14s2. So when it forms a +3 ion, there is no 3d, there is no 4s left. So there is no D subshell in the ion. So which is why it's obviously not transition metal. So transition metal is by definition something that forms stable ions with incomplete D subshells. Why is that important, by the way? The reason is that if it has these incomplete D subshells, there would be certain properties that would be dependent on that. So transition metals are basically elements that are identified or they have certain properties which are caused by incomplete d subshells, which we'll discuss later on. But there are five properties that you studied in O levels as well. So what are those five properties of transition metals?
They are colored, they make like a variable oxidation states, and they have high densities, high melting and
ठीक है.
boiling points.
So they've got variable oxidation states. So they could be +2, they could be +3, or +6 or +7. Second is that they are colored compounds. The proper term is colored complexes in solutions. As the third one is that they have high density. The fourth one is that they have, fourth one, that's they've got high melting and boiling points. The fifth one is that they are very good catalysts. Now we've actually discussed catalysts early on as well in a separate chapter, reaction kinetics, I think. So I'm going to first focus on high density and high melting and boiling points. Why do they have high melting and boiling points? And high density as well. So the thing is that transition metals are basically metals. They've got metallic bonding. What does metallic bonding look like? It's lots of positive ions in a sea of mobile electrons. So let's say that's your typical. So we've got a typical. So a typical transition metal is basically going to look like a lattice of positive and negative positive ions in a sea of mobile electrons. So all of these are positive ions. इसको हटा देते हैं. So all of these are positive ions in a sea of mobile electrons. So the first question is, do you think they have strong metallic bonds or weak metallic bonds? क्या होगा? Do they have strong metallic bonds or weak metallic bonds? Anyone? अफान क्या होगा? Strong
Sir,
or
they
weak?
have
Yeah.
So strong.
Let's say compared to sodium. Is iron stronger than sodium? Well, it's
Yes.
it's it's definitely stronger. ठीक है? Sodium is soft. So it's a lot of positive ions, positive metal ions in a sea of electrons. So now the question is, let's say compared to sodium or even calcium, by the way. So I've got this metallic lattice, and I've got let's say a metallic lattice that's of calcium. And let's say this is iron. Okay, let's bring it over here. So I've got two metallic lattices. So it's calcium versus iron. How do you think iron's lattice would be different compared to calcium? Any idea? Who's going to have the smaller iron? Iron or calcium?
Iron.
And why would it have a smaller iron? Well, pure table. Look at the pure table. Iron is over here and calcium is over here. So why does iron have a smaller ionic radius?
शील्डिंग इलेक्ट्रॉन सेम है लेकिन इलेक्ट्रॉन ज्यादा है तो like
No, what happens across the period? Do the atomic radius, ionic radius increase or decrease when you move across the period?
Decrease.
ठीक है, they decrease. And why do they decrease? Because both of them have the same electronic configuration. Iron's electronic configuration is 426. The electronic configuration is if I take argon, then it's argon, that's 18 electrons up till 3p6, and then it's going to be 4s2 and 3d6, right? For calcium, it's 20, so it's argon followed by 4s2, and there's no electron left in the 3d, so 3d is 0, right? Calcium doesn't have a 3d subshell. But the electronic configuration is kind of the same. The outermost electron is in the s subshell in both iron and calcium. But since iron has more protons, I mean it's got six more protons. It's got more protons. That means higher nuclear charge, and that would lead to stronger attraction, and that would lead to smaller atomic radius. ठीक है? Is this clear?
Yes.
Yes, sir.
So that's the first thing. That the first important thing is that iron's lattice of positive ions in a sea of mobile electrons is going to be smaller in size. ठीक है? So this one over here would be smaller in size. And who's going to have more delocalized electrons?
Sir,
Iron?
iron,
And why would iron have more delocalized electrons?
because it has more number of protons.
नहीं
Like,
होता है कि for calcium, the outermost shell, that's 4s, right? And the 3d doesn't have electrons, right? Actually, there's very little difference or energy gap between the 3d and 4s. So if an atom loses electrons from the 4s, it could also lose electrons from the 3d as well. In the case of calcium, it can only lose two electrons because the 3d is completely empty. But in the case of iron, there's very little difference between the 4s and the 3d. So electrons can also get delocalized from the 3d subshell as well. So there are more electrons that are going to get delocalized in the case of iron. Is that clear? So your lattice is going to have a lot more delocalized electrons. Because that's the second point, that there is little energy gap. So in iron, the electrons are delocalized, or more electrons are delocalized. As electrons are lost from both 3d and 4s. ठीक है? Is that clear?
Yes.
So more electrons are delocalized. So that's the two reasons why it's going to have a stronger metallic bond. You're going to have a stronger metallic bond. Why? Because you've got a smaller ionic radius, plus more electrons are being delocalized as well in the case of iron. So that's a much stronger metallic bond. There's going to be more attraction between the positive ions and the delocalized electrons, which is why iron would have higher melting and boiling points, right? ठीक है? Clear है?
Yes, sir.
ठीक है? Is this clear? Minail clear है? Akshita, Zaina, is this clear?
Yes, sir.
Yes, sir.
Sure.
I said that sums it up, the first one. Okay. So we're done with one property, which is why do they have high melting and boiling points? So we can sum up the next one as well based on this. Why do they have high density? Well, what is density, by the way? Density is what? Mass over volume, right?
Yes, sir.
So why do you think you've got more mass? I mean, you obviously have more mass because iron is heavier, right? Compared to calcium. And not only is it heavier, but it's also smaller than calcium as well. So more of them can be packed together, right? So the first thing is why do they have more mass? Because transition metals are obviously heavier. They've got six more protons, right? Plus, being smaller radius, ionic radius, it leads to more ions packed in the same space. So which is why the density is also higher. ठीक है, smaller pieces, more of them getting packed together, more densely packed. Plus, they obviously have a greater mass as well. ठीक है, is that clear? So we're done with density as well, right?
Yes, yes.
अच्छा, so we figured out why are transition metals denser as well. ठीक है, is that clear? These two things, is that clear to everyone?
Yes, sir.
Yes, sir.
So we're going to do the first one now. Why do they have variable oxidation states? We did that as well because I told you that there's very little energy gap between the 3D and 4s. So which is why if electrons can be lost from the 4s, electrons could also be lost from the 3D as well. Either I'll just post a picture of energy. Here there must be. Yeah, this one. So you can kind of see over here that the 3D and 4s they kind of have overlapping energies. They almost have the same energy. So they almost have the same energy. They're almost the same distance away from the nucleus. So 3D and 4s subshells, they have very little energy gap. So more electrons can be lost. So it depends on the other atom. How many electrons is that capable of? So how good an oxidizing agent is the other atom? So if the other atom is capable of removing a lot of electrons, then iron would lose a lot of electrons. If the other atom is not capable of oxidizing iron, then it won't lose electrons. So hence very little energy gap, so more electrons can be lost. Hence they have variable oxidation states. ठीक है? Is that clear?
Sir, can you explain this again?
The energy difference is very less, no? Like for example, if there's an electron over here, 3s, if you study ionization energies, right?
Hmm.
If you remove electrons from the 3s, it requires a lot of energy to remove electrons from the inner 2p subshell, right?
Yes,
So which is why electrons are always lost from the outermost shell.
बिल्कुल.
But in the case of 3D and 4s, in the case of transition metals, the difference between 3D and 4s is very little. वो जो jump नहीं होती थी ionization energies में, you had this big jump
Yes,
coming. There is no jump. You're removing electrons from the 4s, you're removing electrons from the 3D, that's almost the same. Is that clear?
Say, oh, yes.
So, which is why, plus the 3D has a lot of electrons. So that means you can remove a lot of electrons from, which is why manganese can go up till +7, right? Because you're not just removing the outermost electrons, you're also removing the electrons from the 3D as well. ठीक है, is that clear?
Yes.
Yes, sir.
Acha, so that sums it up. That's
Yes,
so.
sir.
Acha, so we're done with the first property as well. Acha, now this is the important thing, which is, I mean, pretty much the whole chapter is based on this thing. It's colored complexes and solutions. We've done good catalysts as well. We've done heterogeneous and homogeneous catalysts earlier on as well. And I told you why they were good catalysts because they were capable of losing electrons and they're capable of gaining those electrons back. The reactivity is kind of in the middle. They're between metals and non-metals, right? So iron could form 2 plus, and iron 2 plus can gain electrons and form iron back again. Same with gold as well. Gold could form an ion, it could gain the electron back, and so they're not very interested in losing electrons. They're capable of gaining those electrons back again. But anyways, colored complexes. So why are they colored? TK, we'll come to that right at the end. The first thing is, I'm going to start with copper sulfate. And this thing is all about colored complexes. So the first thing is, what's a complex? So for example, if I dissolve copper sulfate, now copper sulfate is like very important. Okay? I mean, everything is surrounded. You get pretty much all questions on copper sulfate. There's cobalt as well. There are other substances, but copper sulfate is the most popular one. Now, if copper sulfate is aqueous, what happens to it? It dissociates. And when it dissociates, it forms copper 2 plus aqueous. And it forms sulfate -2 aqueous. Acha, do you know what the color of copper sulfate aqueous is? Well, you should know what the color of copper
Blue.
sulfate aqueous.
Blue.
That's a blue solution. Which one is blue? Because copper sulfate, remember, is not one thing. It's copper 2 plus aqueous separate and sulfate ion aqueous that's also separate. So what you call blue, it's not copper sulfate. It's actually the copper 2 plus aqueous ions. These are the ones that are blue. Okay, that is what makes it blue. So what is copper 2 plus aqueous? It's actually a complex. It's something that looks like this. It's an octahedral complex. What happens over here is that you've got copper ions, and those copper ions are floating around in water, right? So there is copper ions, and those copper ions have so they have. See, let me just okay. Those copper ions have 3 sides to it, 6 sides. You get something like this. Now, what will happen is that this copper ion is floating in water. Now, water molecules are highly polar. So the very polar water molecules with the lone pairs are going to come in and they're going to start forming dative bonds with the negative part of water will start getting attracted to the copper ion. Okay, and so they're not just floating around in water, they're actually bonded to water molecules. So the ions are not separately just floating around independently, but the water molecule strongly gets attracted to the copper positive ion. Is that clear?
Yes, sir.
Yes.
And it's going to get surrounded from all sides by water molecules. And all these water molecules would be the negative part of the water molecule. So here's another one. So you've got let me just draw all of them. Okay, so you got six water molecules surrounded, and it's not necessarily six, but in this case, with the case of copper and water, it is exactly six. They end up forming, one second. So they end up forming a complex and they bond with six water molecules. You have to remember this, and you should know how to draw this as well. They're going to ask you to draw this. What is the overall charge on the entire thing? The overall charge would be +2. Why? Because the water molecules are all neutral. But the copper in the middle has a +2 charge. The copper in the middle, so overall charge is going to be +2. The other way to write this is copper with six water molecules, and you use a square bracket to represent a complex. It's got an overall charge of +2. This is known as hexa aqua copper 2 complex. So the thing that you call copper 2 plus aqueous, it's actually this thing. ठीक है, is that clear?
Sir, can you explain again ये 6 क्यों सिर्फ 6 क्यों करेगा?
Because you run out of space. It all depends. It could be four as well. It could be five. It could be any number of complex ligands. I said this thing. Let me just describe what the naming is.
Oh,
Uh, Six is, Manjuta, if you had like really big molecules, would you fit more of them around it, or would you fit fewer of them?
fewer.
Fewer. If you have a big one, so you'll run out of space, right? Okay, there's a big
Yeah.
molecule coming from the top. There's a big molecule coming from the bottom. So you won't have any side left. So it all depends on I mean, mainly it depends on the ratio of the ions or the size of the ions. If this is big and these are small, then you can fit a lot of them around it. If this is small and the molecules that are coming in to bond with it are like really big, then you can't fit a lot of them around it. Okay. So is this part clear?
Yes.
Okay, why in this case it's six, right? So now this thing, there's a few names that are given to this. This whole thing is a complex, and this thing over here, ठीक है, जो water molecules are specifically, these are known as your ligands. So that's your ligand. Now they're going to ask you about definitions of a ligand. What's a ligand? It's a species that has lone pairs. So it's a species. It could be a molecule. It could be an ion. For example, it could be ammonia as well. So it's anything that's got lone pairs and which is capable of datively bonding. So which has a lone pair of electrons and datively bonds to metal cations. And as a result, they form a complex ion. See, again, the definition over here is important. Okay, they're going to ask you to draw this. They're going to ask you to name the color of this. And they will ask you to identify what the ligand is, what is the definition of a ligand, and what's the definition of a complex, by the way. It's something similar. It's an ion formed. So what's a complex? It's an ion formed when a central metal cation datively bonds to a ligand. So when a central metal cation, it datively forms bonds with ligands. So that's what a complex looks like. That's just one of the complexes. And this is specifically an octahedral complex. Why? Because it's forming six bonds. If you know the shape of the molecules, so this one is an octahedral complex. Uh, the bond angles over here are 90 degree. Okay, all of them are on the axis. And so that's it. Okay, that's what one example of an octahedral complex looks like. Okay, one bond is on the top, one bottom, one on the x-axis, one on the y-axis. Okay, is this all clear what a complex is? Is this clear?
Yes, sir.
Okay, everyone, is this clear?
Yes.
Yes, sir.
So ठीक है. Just remember you'll be asked all of this, okay? So फिर we'll continue this in the next class. So we're going to study other complexes as well. Okay, so there are many complexes we're going to study, and then complexes what change. Ligands could be lost, they could be gained, they could be replaced. So we'll do reactions where one ligand gets replaced by some other ligand, and so you can replace these ligands as well. So we're going to study all sorts of different complexes and how one could be changed into another one, and so on. Those are known as ligand exchange reactions. Okay, so we'll do that in the next class. Okay.
Okay, sir.
So,
Okay, sir. Enough is.
okay, take care.
Thank you, sir. Allah Hafiz.
Fizz.
Thank you, sir.